I think we're ready. Ron, hello. How's it going? I'm Agent Ultra, and I'm here to hack some Haskell with you for the next couple of hours. For the project we've been working on in the stream, we've been building, we've been learning about how to implement an algorithm called wave function collapse. This is an algorithm that generates textures, mainly, is what it's used for often, but can generate all kinds of stuff. 3D geometry, poems, whatever you want. The whole idea with it is that it's kind of like a constraint propagation solver. You have a bunch of rules that constrain the output, and then you have like some randomized inputs you initialize everything to, and then you start solving the problem, sort of like a Sudoku puzzle, right? You pick value, you start cutting off other possible choices based on those constraints. So let's open up the code and get back in there and get working and have some fun with this and see if we can figure this out. So I think I'm getting near the end. I did attempt quite some time ago to implement part of this algorithm just based off my own understanding of it, and I think I went wrong somewhere, and that we ended up with like an infinite loop during the propagate step, somewhere in there. So we went back to a tutorial implementation, just to try and implement their version of the algorithm to see if we could learn something by comparing the two approaches, basically, by implementing theirs and then trying to figure out where mine went wrong. And then maybe I'll go back, see if I can implement my version of the algorithm after learning whatever I'm going to learn. We'll see. We'll see. Maybe we want to do a different project. I don't know. After we get this working. So, let me fire up the builder. This is the code. So I use the stack tool for my projects, as if you've been watching, you all know. But if you haven't, welcome. Let's go. So use the fast, and I use the file watch switches with those, and voila. Okay. Oh, actually, instead of build, I'm going to use a test runner. So you get the same options, but just test. All right, we have an undefined array element here, as I recall, from before my vacation, which is a while ago. So this is an initialization error, as we discovered on the last stream, and not an indexing error, which looks similar but is slightly different text here. So undefined array element means we're not initializing one of the arrays that we need to initialize in the test. So I'm going to go over the test code and just check that. We're doing run wave here. This is kind of like my sanity check test, because it's like this algorithm seems to have a lot of moving parts to it. And so I kind of want to just make sure that, like, if we start with an input texture, we can generate the patterns, we can cut the patterns out from it, we can initialize our initial state, we can run the algorithm, and that at least if we run the algorithm, the output texture we get should be different from the first input, the initial wave state that we start with. So we've done something. It might not be the greatest output, it might not look the way we want it, it might be looking weird or whatever, but at least it finishes. All right, so that's what this will test, to make sure that it finishes and that the algorithm at least changed something, right? Did some work, I made some progress. And then we might need to like actually see some results and tweak and stuff from there, but yeah. Okay, so when we get the input texture, this one's all initialized just fine. I think it's probably in the init wave state, perhaps. Possibly somewhere inside running the algorithm. I had some debug trace statements in there, it looks like, from last time. So let's start there. Get cell at. Okay, there we go. Boom, get cell at. 1, 3. In range. We checked maybe at, right. It's starting to come back to me a little bit. We did check maybe at with the index 1, 3. We check if it's in range of 0, 0 to 9, 9. It should be. Excel pattern enabler count 15. And that's this deploy trace here. No, that's fine. Jumping over to maybe at. So we should see after. But we don't. Right. Okay. Make sure I got you, chat. There you go. Okay, so let's see. We use maybe at for collapse and cell at. Looks like we were thinking it was in cell at. Okay. I'm going to bring up my little REPL and just experiment around a little bit. I think probably tried this on the last stream a bit, so if anybody remembers, let me know. We want an array like we construct here for the grid. Actually, I'm gonna plus data.array. Like that. Okay, so now I got data.array in scope here in my REPL. That's good. There's our list array function. To construct one, we're gonna bind it to R. Okay, that takes our bounds and our initial list. So we're gonna go 0, 0. And 2, 2. So it should be a 3 by 3 grid, right? Now our list, we struggled with this a little bit. I think our list is just a flat list of elements. These, no I's in there. Alright, so we should be able to go A, B, C, D, E, F, G. If I could type, that would be great. H and I. Okay, there's our full array. That's just a type defaulting to integer for the indices. So if we try array, bang 0, 1, we should get B. All right. Zero, 2, 0, 3, that should be out of range. It should be 0, 2. That's out of range. Okay. That seems all reasonable, right? Like, that's how it should work. Go back to maybe at... that one should show, which it does, the ray bounds right there, 0, 0 to 99, so it should be in that. So we're definitely here for sure. Okay, so whatever, it's got to be something that we're initializing in here. So let's check. Let's go back to the test. Go over here. Bang, we get the patterns, input texture with 3. Do I have debug to trace in here? I don't. So let's get that. Trace, qualified. Debug. Okay. And we will trace here. Just going to show the pattern result. Okay, and then our initial wave state. I'll do that as well. Yeah. I don't know if I'll be able to show the wave state. I don't know if it has a show instance. We'll probably check that quickly, but. New. It doesn't. Okay. But we can just show a part of it at least. So let's show the grid. I think that does have. Merp. We'll go back off. Bad habit. Because on my work code base that I work on, and during the day I end up using, we use post positive position or whatever for that keyword. Silliness, but it always flips me around because almost all the open source Haskell code I see doesn't use that one. So I end up working with it all day. So then when I go on my stream, my brain gets to flip around first. Okay. So we get uncaught exception, undefined array element, before we even get any debug output. I'm gonna force a rebuild just to be I'm pretty sure that's thing. So it might be our initialization code that's doing this to us here. If I turn off this debug.trace, like this. Okay, so if I take that out though, temporarily, do we go back to our debug output? Yeah, we do. So our pattern results are fine. Okay, so it's definitely got to be in our wave initialization code somewhere, our initial state. Interesting. Okay. Let's go. Let's dive in. Grid, we use make grid, grid width, grid height. Pattern resolve frequency hit adjacency rules. And then generate the C, we make a standard generator. And we build our heap, our entropy list. By getting the array from grid. That might trigger things, perhaps. Building our entropy list. Just does heat insert, heap insert. I'm gonna pull that out. Bang, bang. Okay. In here. Good. Let's take a look at that one. I don't. Come on, let's go. Undefined array element. Okay. So our grid isn't getting initialized properly. Let's visit the old make grid. So we call list array just like we did at the REPL. With the width and height we want -1. We call repeat make cell pattern result frequency and adjacency rules. I wonder if if repeat isn't sufficient here. Let me go to my REPL again. Let's make an array. 0, 0 to 2, 2. But we're going to just do repeat A's. Now if I do array bang 0, 1, what do I get? A. Array bang 2, 2. Okay, as I should. Hit 1, 1. Like, that should all be fine. Do I have enough grid and make grid and scope? Make grid. It's not a scope. Slow down. Now I got it, right? Okay, so that expression should work at least to produce all the cells that we want. The possibility maybe that this expression here is not right. still lingers, and depending on what's in make cell. Right, all possibilities is fine. It's an array, but yeah, shouldn't be that stuff. Okay. Let's see. What if we use a damn undefined array element? Curses. Maybe it's here. I don't think so necessarily. No. We do get back all of this debug output when we... That one in, but if we undo that, that'll go away. Noosh. Okay, that seems to stay there. Okay, so maybe it's on one of the arrays in Excel that's actually the problem. Not being initialized. Or getting something, or... Yeah, not initialized. Possibly. Cell enabler count. Okay, let's take that debug trace out there. Let bind this. Oh, debug.trace here. Enabler count. We'll show A and return it. All right. Whoa, formatting. That's just the pattern result. Okay, so maybe that's like still returning stuff. We're still getting the failure, but we're not getting our trace here. Where's cell at called? Get cell at. Let's get cell out. It's called get neighbor removals, modify cell at. Is collapsed. And propagate. Okay. This could be possibly. Pop one in here. Are you something ridiculous? And still, why is the wave state grid not initialized properly? A little question mark in there, and show that well. I need trace M's for this. Sorry. Beep, beep, beep. Beep, beep, beep. Oh, I don't even get there. Probably don't even use that code. Yep. Mm-hmm. Okay, propagate collapse. We choose a cell, collapse at. Maybe at. We gotta get further than that. that one, get rid of that one. Okay. So it's definitely gotta be... Gotta be something we're initializing that isn't being set up properly. Make... Let's jump back over to make wave state. It's possibly this grid. We'll do make wave state start. Trace M. Wave state after. And we'll pop the grid there. Possibly we'll see make wave state start, but we won't see after. Oh, this isn't a do block. Go here like this, make that a trace. We'll take this over here. That. And we'll do after here, pop that there, and get rid of the M. I think we can put these in parentheses. And that should get us there. Okay. So we hit start. And we can't then, because we don't have a grid. Okay. Don't think it's this. Just in case. Do it that way. So it might be... It's just such a common source of these things. Okay. No. It's got to be those two. So it's got to be in make cell then. All possibilities. Could be just an array, everything true. All the indices from 0 up to pattern result max index. Speaking of off by one errors. I wonder if it's all possibilities. Or all apologies, I don't know. Okay. It's the pattern result max index. Comes from the pattern result. It's an integer value. Create the pattern result. And patterns function here. Okay, we do chop off. So the max one would be the Yeah, the off by one, whatever. Suitable as an array length. Max index or array index. So, that one should be fine. Possibly. I mean, that's a point of concern there. At least it's doing something with indices there. So that could be it. Just with sum of weight log weight. Takes in an array, gives a float. Just calls the associations. So it's not looking into an uninitialized array. Set x here. Relative frequency. Looks into a map. So that should be fine. Total weight. Also, possible tile frequency possibilities. Jump there. Again, we just take the association list of the array. Just do some counting, so that should be good. Jump back there. So it could be all possibilities, maybe, though doubtful. And last check is to like make cell pattern enabler count. Or pattern enabler count, right? So it goes up to 0 pattern result, max index as well. And for D directions. I do believe we get to the count part. Although we don't here because we're forcing the grid. Although this expression does have one possible problem with it. And that our bounds here are the 0 to pattern result max index. And the list we're generating is a bit bigger than that, I believe, because the combination of these two here. With D and directions. That could be a possible thing. We'd have to multiply that by the D and directions. Although, yeah, I don't know. Yeah, that might be, I don't know if that's going to be the issue, but. Doesn't seem likely. So that function comes from our friend. Yeah. Vector. Yeah, no, that's not it. Counting enablers. Enable counts. A vector again, yes. So initializing that creates a new mutable vector. Mutable counts. Iterate for all directions. Take the adjacency rules. Get the compatible tiles for A and direction. Modify counts. By direction field, in direction, and add a 1 to it. So we push that onto ret. So all we're pushing onto for direction in there, pushing on the ret. Okay. We're only doing one of these for every pattern. That's definitely a bug with this. That's not a direct translation here, so we can fix that. The output of the length of this vector should be at the end after we push all of these. The length of num tiles minus 1. Or pattern result max index. I'm happy with that part. I think it's the D we have to take out here. And then it's init pattern enabler count. We're going to take the direction out of here, here. And it's in this fold that we're going to increment the directions of our initial pattern enabler count for those compatible tiles. How are we going to do that here? We could do it in this function, maybe? We just iterate over each direction and directions. We have a foldable 4 underscore. Gives us an applicative of unit. We need direction for both of those scopes. Gross. Bear with me for a moment. Yeah, now the context of the applicative here is not working with our type. For init pattern and enable account. Okay. So how can we construct this without using mutation? What do we have in scope here? We have an int, which is our pattern index. We need to return a pattern enabler count. If we look for pattern enabler count, yeah, initialize that all to zeros. One for each of the directions. Pardon me 1 second. Haskell Cat, would you see what you do on this? Oh no. There we go. Good times. Good times. Okay, we're back. So pattern enabler count there, 0, 0, 0, 0. Okay, that's good. And then here. Yeah, it's because we need to get the compatible adjacency rules for the direction. Hmm. Oh wait, what if I use iterate? Package. Oh, Google. So if I get an A to A function and some starting A, and I continue to produce a list of A's, repeat applications of f to x, yeah. No. That would return the applicative of it if we did 4. All the directions. Direction to FB. F this to B. That would give us a list of... I mean, the other thing we can do is follow that code literally and use mutable references ourselves. Just to emulate the code. Which is silly. I think there's got to be a way to do this. What am I missing here? Right, all we need to really do is for each direction, get the compatible tiles for that direction. And we're just incrementing a number. I guess if this returned the tuple of the direction and the tile, in our implementation at least, that might do it. Yeah. Okay, so compatible. Well, then I still have to put direction into it. Yeah, the type doesn't really make sense of the shape for that. So I do this as a list of things. Alright, I get the compatible tiles, patterns with my adjacency rules, pattern index, and direction dir. Alright, this function here would have to do a list of pattern indexes to pattern enabler count. And if I pop that in here, DR2, and we change the shape a little bit, and we get a list of pattern indexes and directions to pattern enabler count. That list of pattern indices. From the adjacency rules, get the adjacency rules, map it to a list. Filter on the second, so only the enabled ones. And we filter again on the enabled ones for an adjacency key with pattern A in the direction the same as our arguments. And then we take pattern B off of that key. So this could be an empty list. Very much so. In which case we would want to default to 0 there. Compatible tiles for that direction. Otherwise, it's just the number of the length of this list, isn't it? Right. So this iterates through that list of compatible tiles, but throws away tile B just in order to increment by 1. So really, it's just the sum of these. The length of this list, right? For that direction. That tile enabler count direction. So I'm going to keep that here. Pattern enabler count. It's just an array. Hey, Twitch TD. Not quite as in physics, but it does get the inspiration from it. It's more of like a procedural generation algorithm. I'm using a lot of like popular roguelike style games, that kind of stuff. Let's see how. Yeah, so the name is inspired from like wave function, like the wave function thing in physics and quantum physics. The idea is, I guess the idea is you start off with a big grid of variables that can take all possible values. You observe a value in one, or you pick a value for one, and then you collapse the other ones based on your adjacency rules, the possible values of the other ones, until you've fully collapsed everything down to one value. So it's sort of like, I don't know, the Schrodinger's cat, right? They're all possible values until you pick one. So the goal is to try and flatten out that grid so that everything has one. And I just use a little bit of randomization to do that. Yeah. Right now, I'm just running into some array initialization problems with my sloppy code. So we're just trying to figure that out. So I think otherwise, once we get past that, hopefully will just work. And then we'll just be hooking it up to a graphical front end so we can see the results. Okay, so our cell enabler counts we have to initialize. That's an array of values. And so that array of values for each built out is an array of for each direction. Just like this. We want the sum of the list for each value. I mean, complex games are going to make things hard, regardless. I think it certainly does kind of make things a little challenging in some respects. Like this learning from this tutorial, because it's written in Rust, it's a very procedural language, so I'm like trying to translate this into Haskell in the most straightforward way possible. Which I could go full, mutability and use mutability here to build this thing if I want to. I think it would just make my code even more complicated. But stuff like that kind of makes you go, ugh. But I'm sure if I did it first principles from Haskell, maybe it would be a little bit better, but yeah, it could in some ways. But it also makes things easier in others. Well, you can do unsafe stuff in Haskell too. You don't have to completely give up. Yeah, maybe we should explore, I don't know, mutability in Haskell sometime, because, like, it's not off talk about, but you get the ST stuff. And that lets you kind of do all this kind of stuff. We can create a reference to a data thing, and then you can modify it in place using mutation. That sort of stuff. Yeah, where I find it really does shine like quite a lot though is like multi-threaded stuff, concurrency, super good, runtime systems, amazing. You can write really, really high-level code that compiles down to pretty efficient machine code. Barring the runtime that you're always going to have in all your executables. It kind of does, like, optimization kind of does what you would almost expect. Which I might do a stream on sometime too. I was kind of fooling around with taking the object dumps of, like, Haskell executables to see if I can, like, kind of parse what's happening there. Yeah, so it's pretty interesting that way. Yeah. Exactly. So I think the way to go here is just to not use mutation here. I think what it is really is just we can build this array list here by taking the sum of these adjacency, the compatible tiles that we get back from going over the directions. So that's all this code is doing, really. It's just doing it in a long-winded way. And I think hopefully that will get us what we need. All right, that push is basically here. And this expression, it's just this part. So pattern enabler count. We can put the constructor there. We can list array this 0 to length of directions -1. And then we compute the sum. or the length of this list of compatible adjacency rule. Basically, adjacency rules, get rid of that. List arrays, your bounds. That's the bounds of the array. So like the first index and the last index in the array. I'm not super... Arrays are kind of a pain in the ass in any language, like even in C. But there's like good and bad. It's not very Haskell-y to work with them. Yeah, explicit indexes, yeah. But you get a little bit of safety out of it by using Haskell, but not much. Yeah. I don't know how I feel about using them. I'm kind of on the fence. Because you end up with these like when you get like index errors, if it can't catch it at compile time, like you get these really bad like runtime exceptions, which runtime exceptions in Haskell kind of suck. Kind of the worst part of it. So we try to avoid them as much as possible, I would say, but when you use arrays, you kind of open yourself up to the possibility, I guess. Yeah, 1 to n. Yeah, exactly. Whenever I'm like doing stuff in Lua, that always throws me off. There's one indexed arrays. I'm just decades and decades and decades of 0 indexed arrays. And then I try Lua and my brain's little... Okay, but we still need for each direction here. Oh yeah, actually, so for each direction here, we're mutating the counts here, and then we're pushing that into this outer scope here, this outer variable. This ret will end up with a tile enabler account. For each direction. No, one tile enabler account for each tile. Yeah. And so the counts for each tile direction combination. Yep, no problem. Yeah, we found like there's a couple of small minor nits with the Rust code, but this is what I'm trying to compare my original first pass at this to by implementing it this way. Yeah, so it's going to return one for each tile in num tiles. Return one ret. I guess that builds up the vector. That's weird, actually. I think this is probably supposed to be on the outside here. Return ret. That doesn't make... yeah. That seems like that might be a bug, potentially. Because initially we're going to come into this for loop, we're going to initialize tile A to like 0. Do all this stuff. And then we're going to return. Here. I don't know if that's like in Rust that's a return, like an early exit. That means we're only going to get one tile enabler count. Okay. I'm starting to think maybe I need to go back to my original plan. I have to go back to my implementation. Okay. So I think that should be on the outside anyway. So let's go with that. And so we just need this inner loop here for each direction. Ugly at first, but if we make progress, that would be good. Ooh. Almost, actually, yeah. That is progress. Because this is a completely different error here. Okay. This is a pretty simple error, too. Okay, so it was our pattern enabler counts code, probably, that looked like it was the issue. Oop. Oh, back there. Cell pattern enabler counts. Yeah, that's what I think too. Just needs to be moved up. Oh, one scope. There's a couple small ones like that. Like tile B here is initialized but not used. Not a big deal, but could be cleaned up. There's another one here. Opposite directions not used as well. Probably just a result of like some refactoring and then making the blog post. You know how it is. We all do it sometimes. Okay. So I think that gave us progress. Now we just have to fix this problem. 552. I'm gonna jump over there. Here. Yep. We're missing a record field here. We're gonna put something there. This is collapse at. And I'm gonna put I think we have the pattern results and adjacent rules in the scope to do that, maybe? things. We need... Go about all the things. Pattern results. I have one. I got relevant by invalid. No, don't have that quite in scope. At least not where I can see it easily. You have a C cell which would have them. But when we collapse a cell, I think we do have to pick or update the pattern enabler counts, if I'm not too mistaken. Yeah, we have to decrement it for that particular direction by 1. For the compatible tiles in the adjacency rules, compatible tiles list for that direction. Then we decrement by 1. I gotta check one thing though. Do I call collapse at? Call it in one place. Propagate collapse. Propagate. I think that might be dead code. Which is what I'm getting at here. That's where you do the decrement neighbor count. Yeah, I think that can just be removed. This might all be useless. Remainders of attempts past. Lapse, comment region. Alright, collapse wave calls that. Okay. Okay, so I do need that. Damn. Curses. Well, Twitch TD, it's been a pleasure. Have a good dinner. And I usually do these on Tuesday evenings, starting about 8-10 p.m. in the Eastern time zone. So, otherwise, check out my socials too. I've got I archive all of my videos to my YouTube channel. I'll check a pop in the chat. But otherwise, yeah, you know, give us a follow and that'd be great. And yeah. Oh, thanks for the follow, actually. You got ahead of me there. Awesome, I missed it. Sorry about that. But yes, thanks for watching. Hope you have a great dinner. We'll talk to you soon. Okay, yes. So we have to put something in that hole. We need the patterns. think because the propagation step maybe already handles it, it's probably fine just to put the cells. Existing ones in there. Sorry. Cell. Oh, that's pattern results, isn't it? I think we have to get that from the wave state. If we store it in there. Ah, we don't. Well, we could. That would be super easy. And then... what's the other banding? Adjacency rules. We do have that. State pattern results. Oh, but then we have to type parameterize wave state. That's gonna be super annoying. Oof. That's gonna be gross. I'd like to try to avoid that if possible. There's just no way to... So why do we use collapse cell? Well, this would be actually pretty easy. We could bypass this, I think. All we care about are those two fields. We can leave the rest the same. So get rid of these. We turn this into a C such that that gets rid of those. And then what do we end up with? Oof. Something going on here. Possibly back to another infinite loop. Looks like we've got rid of the array initialization issue. That's good. Let's review, shall we? Okay, so we fixed the length, the array indices on that one. And updated make cell pattern enabler account. So we just have some debug traces to remove. Collapse cell we failed. Okay. So I guess that was it. It was the adjacency enabler counts. Cool, 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 cool. And we'll just remove all instances of our trace. We don't need to bind the results since we don't use it. That one. Anything here. This one. And this one. Got a lot of them. Skadoosh, 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 skadoosh. Skadoosh. The scope of that modification enabler counts should be I guess outside of there. Okay, a few more. Bang. Bang. That one. That one. Word. I think that's all of them? Okay, cool. Alright, so let's create a commit for that, at least. Not out of the weeds yet, but we're getting there. And we should probably also remove it from spec as well. What was it? Neighbor enabled counts. Okay. And let's get that test going again. Super. Progress. Okay. That's one of our own, so that's okay. It's not quite a runtime exception in the same way as like an IO exception. Okay, so we couldn't find a pattern to collapse to. At least in that. That's pretty decent, actually. I mean, it might be because we haven't implemented things properly yet, but we're getting to this line here in collapse at. So in this one, this is the base case for when we run out of pattern indices in Go here. Go is used.
It's appropriate to call them human anymore.
Oh, just above. And pick pattern. So in pick pattern index, we're looking at the cell. We're picking a random one. Remaining ran between 0 and cell total weight. And P's is possible patterns for cell possibilities. Remaining. So when we have some P, some pattern indices, this all stuff. Okay. So are we could be hitting this because we're just initializing Go with the empty list. So possible patterns. Could be returning an empty list. Take the reassociations. We filter on the second value, so if it's enabled or not. And then we take out the keys, map the first of the reassociations. Take out the keys of our remaining. Okay. So that it's possible we can get into this state. We change the seed. Do we get one that succeeds maybe? Or is it always this? Because that would kind of, that seems like that would, if it's always that no matter what the seed is, that would be an error. In our code, I mean. Okay. Alright, so I think that's probably something in our collapse code that's doing this, possibly. We're back to it. Trace M, pick pattern X. And we'll show these. Okay, so we get to pick pattern X here, and by our setup we have from 0, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we have 16 elements here. And the second call to it, we eliminated quite a few. 0, 2, 4, 6, 8, 10, 12, and 14 are remaining. And then we hit at the base case. Although these could be two different cells. I wonder if there's a... Maybe there's a way I could put in here somewhere that, like a little assertion that we never go down to an empty list of possibilities. Should always be possible to pick at least one. Although we can run into contradictions. That is a thing that can happen. So maybe this... But this doesn't seem like a contradiction case because, like, I changed the seed and, like, we're not finding any. Before I dig too deep in, let's just change the input patterns or the wave state, the size of the output texture a little bit. Just to make sure, but I'm pretty sure we're gonna get the same result. Might take a little longer to get there with the 2020, but... Yeah. So I think those are probably different cells were collapsing. And then somewhere we're collapsing them, at least one cell down, like all possibilities are false. So the output grid is changing the amount of cells we're going to and collapsing, which is good. Okay. Yep, run window. Let's go back over to Emacs where I can actually, those things make sense. Okay, cool. And, collapse cell possibilities. Here, okay. I'm gonna bind that to remaining keys, put this expression up here. Trace that out here. And show keys there. Okay. So there's one true, everything else is false. Okay, so that's good. That's kind of what we expect when we collapse cell possibilities. There should be always one true in there. Everything else is false. And then... out of possible patterns, wonder if there's a way I could say, like, when all false. I suspect, because what I'm suspecting right now is that when we go to pick pattern from cell possibilities, we're coming across a cell that has all collapsed, like entirely, and it shouldn't. I mean, that can happen, but it shouldn't. And here so much? Shouldn't be so consistent. So we call pick pattern. I think P's should be non-empty. When null P's. Let's see if we get that runtime error there. Nope. Okay, so that holds, at least so far in our example. And if I maybe bigger, so that we can hit this a bunch of times. I guess we'll probably not see that error trigger. No, we don't. Okay. So, what else could it be? It could be here that we're inappropriately, or we're failing to update the relative frequency, the cache sums and weights. Not just because of the frequency hints. Like, I wonder, obviously, if P's is never null, when we apply go to remaining in P's, that means we're getting to this branch because we're recurring to it. And the only expression in here that recurs on P's is go here. So we're finding that remainder is never being less than weight. Let's check that out. Let's go wait. And go remainder. Yeah. So we start off with go 95. our weight is consistently 8. It never seems to change. And we do decrement the remainder, 95, 87, 79, 71, 63, by like 8 every time. Remainder minus weight. I guess we do it just enough times that we never actually hit our pure P condition here to pick this pattern index. Okay. Choose tile. Okay. So for this seed, we're picking a random number between 0 and the cell total weight. Sum of possible tile weights. Okay, so we calculate a new weight in this code from the frequency hints for every possible tile index. So all the possible tiles that we can choose from. We get the relative frequency for that. And we do mutate remaining to be less than or equal to weight. So this weight value should fluctuate a little bit. So that's kind of one thing that's kind of suspicious about this. What we have is that it's consistently 8. So I'm probably not doing something right in the code there for that. I don't know about this. But, oh, hey, welcome back, Twitch TV. Yeah, I don't know how much time I got left, actually. It's getting a little bit late. I usually end the stream around this time. But I really, really, really want to conquer the last of this. Okay, so we did make some progress while you were away. We got the array initialization bug figured out. Now we're just getting to a point where we're getting to this error base case that we think we shouldn't be able to get to. Does Haskell have loops? Yeah. Yeah, it does, Goku. For sure. Ways to achieve iteration, there are a few. Yeah, it does. So like in a lot of pure code, you'll find like just recursion, which you can translate directly into a loop, back and forth. Although recursion can sometimes get hairy if you have a lot of variables in your loop, so best for simple stuff. But you do have for loops as well, and different flavors of those. Sorry, I was adjusting my keyboard, and now I've adjusted my whole editor size. There we go. Okay. No problem, Goku. No problem. Love answering questions and helping out with that stuff. Yeah, it does have for loops, and it also iteration, which is more like, as we saw, actually, we looked up the function signatures for it earlier. Pardon me. So like you've got for, you've got iterate. So this generates an infinite list, like successively applying this function to your initial seed value. Yeah, I love formal methods, TwitchTD, for sure. At work I use it occasionally when the time calls for it. I use TLA Plus for modeling various things. And I've tried my hand at peer improving. I'm not terribly good at it, but I'm learning a little bit as I go. Yeah, you got to iterate and for loops. You got for loops for effects like form and stuff, where you just want to iterate over a collection and do something with it and all kinds of stuff. So yeah, lots of different ways to loop. Yeah, I think like formal methods is an umbrella term for a lot of technologies, and I think a lot of them are actually becoming a lot more popular pretty quickly. Like model checking seems to be catching on a fair bit, I would say. And the tools have gotten a lot better for doing that. Like I'm not a university trained person, and a lot of people in industry think formal methods, you got to be a pointy-haired academic in order to use them and have like a PhD. But if I can pick it up, I think a lot of other developers are doing themselves a disservice by not and avoiding it and kind of believing those sorts of myths, because it's actually really useful and pretty straightforward to pick up. It takes a little while to learn, like anything useful, but it's definitely worth it for sure. But yeah, you kind of run into that friction, which does kind of keep things from moving quickly, I suppose. But it's coming along. You know, I think there's a group at Amazon that uses it now in the AWS team more comprehensively. They're entirely dedicated to running large models constantly. So they're building like tooling for that. Microsoft, I've heard, uses it on Azure a lot and things like that. So. And a colleague of mine does formal verification of, they build like a software hypervisor. Yeah. And so they're actually doing like soup to nuts, full, like fully proven, not just model checked. Source code for the whole hypervisor, which I think is super neat. But yeah, so there's the mutable version of Fibonacci if you wanted to write it in Haskell. Yeah, dry up edition. Certainly. Okay, so there's kind of a bit of an issue there. I'm never getting to this branch on line 567 here. Okay, I'm going straight to here, which we shouldn't be doing, according to this, which is where I cribbed this from, I think. Yeah. Okay, so first thing that's coming up to mind, relative frequency. I think we have that. Just gonna check that definition. Oh hey, Limitson. Yeah, so wave function collapse is like a procedural generation algorithm. I think it was probably popularized in game development. A lot of games use it for generating procedural levels and textures and things like that. Other creative uses of it go far beyond that, but you could use it for a lot of different things. Yeah, the comparison. Alright, so the comparison here is if it's greater than or equal to weight. Like we could flip these around too. Then it decrements remaining. Right, but then keeps going to the next possible tile index, gets the weight, right, and so on and so forth, until we hit this return case, which apparently should be always hittable. So like early return type stuff is a little tricky, translating this into Haskell. Not, should be easy, but it's late, and I'm like running out of energy here. Yeah, actually I might have to go that, but I think this is where it's going to be. Map plus take one. Yeah, actually, oh, hey, good suggestion. Yeah, that would be... I think that's what you mean now. So if we go recurring on the remainder of pattern indices here, but if we map over the pattern indices on remainder, we'd have to statefully update remaining, decrementing by the weight. And then we could take one. So we could do that with a fold, I guess, and then take one from that. I do, Imlinson. Hopefully I'm saying that one right. I do work in Haskell, my day job. I'm not doing stuff like this. I do like fintech stuff, which is a lot simpler. Yeah, you don't want to waste CPUs doing processing full list. You want to kind of quit early. So we want to quit when we hit this condition, basically, or when we fail to hit this condition. Well, that's cool, though. I hear Kotlin's pretty good. We have some Kotlin developers, because we do an Android app, and I think it's all written in Kotlin. Scala's pretty cool, too. I haven't done a whole lot of Scala, but I tried learning it early on. It's fun. Fusion, maybe. Twitch TV. So we're thinking like instead of go recurring on the remaining P's of the possible patterns, mapping over that. Or in here. Leaky abstraction levels. Yeah. And I think they're mostly our fault. Most of the time. We can have better ones, though. And doesn't mean we shouldn't try. I think abstractions are really, really useful and kind of like the bread and butter of our job. But, I mean abstraction in kind of like the more mathematical sense than the like indirection and like programming patterns sense. Yeah, no, Haskell's not perfect by any stretch of the imagination. It's such a low bar to clear, though. So it does pretty well. But yeah, there's still lots of room for learning and experimentation and stuff. I don't think we're nearly at the end of languages. Not even close. I've done a little stuff in Lean 4. I wrote Lean 4 Hackers a long time ago now. I think it's on GitHub. Is it Lean-4-Hackers? Anyways, it's just an article on setting up Lean for programming. Yeah, so dependent types is an interesting one. What was really cool about learning to hack with Lean 4 and make programs with it is that it's good at generating code that is surprisingly fast for such a high-level language. Like, sorry, I just dropped something again. Ah. Oh no! Everything. Okay. What am I even doing, Cap? I don't even need it. I got batteries ready. It's all good. Anyways, so the thing with dependent types, though, is that you don't want to use them if you don't have to. Like, you really don't want to. So even if you go to Lean 4 Hackers and you check that article out and you look at the program there, I made like a word count thing here. And on my like really crappy laptop, I compiled and ran it and compared word count to like the stock word count that ships with whatever operating system I had there. And it's not like super close. Like system WC is obviously going to be as fast as it can probably be. Right, but yeah, for like our high level dependently typed programming language, pretty close. Like, not bad. And I'm sure like it obviously doesn't do everything that WC does, because the libraries and stuff are pretty limited in Lean 4 for this sorts of thing. But like, if you could add on to it, and I could reasonably see like you getting within a decent ballpark is still supporting all the major features. Is it going to be useful to write WC in like a dependent type programming language? Not really, because we don't actually use dependent types a whole lot, or at all, maybe even in the program itself. Just some structs and stuff, a lot of partials and whatever, because like you have to be, in order to program in a language like this, you have to be like total. You can't be partial like Haskell is. So you have all these partial keywords everywhere. Just be like, yeah, this can error out basically. I'm not going to prove that it terminates. Yeah. Yeah, that's an interesting thing about church and like um, Turing and stuff. Like they all existed relatively close to each other. Church famously was kind of first with his paper before the Turing machine came around, but like not by much. But I think it was I was reading the history on it a while ago. And I think Clean found an issue with the original lambda calculus, and Church came back with the simply typed lambda calculus quite a while later. And my theory is that in the intermediate time between the simply typed lambda calculus and figuring out evaluation and reduction and all of that, Turing machines had already kind of established themselves as the kind of benchmark for gauging the performance of algorithms. At least that's my theory. I'm not sure on that one, but I think that's kind of why they sort of won out in the end. But I do feel like Church was really onto something. Maybe he didn't really see it that way himself, but yeah. There are interesting newer computer processors that are really doing stuff with this kind of stuff, but it's kind of always behind, I guess, the times in terms of like how we architect modern systems and stuff. But anyway, neat things to think about. So yeah, yeah. But even dependent types is one of those things. Like, I've heard people recommend to me that they should avoid them as much as possible, as you can tie yourself into knots trying to overly specify everything in the types. And I think that's kind of where Haskell hits the sweet spot too for programming, is that simply typed seems to be good enough for a lot of things. And you can do dependently typed in Haskell, and you can kind of keep it constrained to small amounts, which is probably a good thing. Yep, for sure, Twitch, for sure. Anyhoozle, I'm running on and rambling and having a great time with this, but I gotta run. This is running over time, so we're gonna have to revisit this next week and try and fix this. But thanks for the chat. It's been great. I hope you had a great time following along, and we'll see you next time. So for those of you who are just tuning in or haven't seen the stream before, I usually do these on Tuesday evenings at about 10 after 8 in the Eastern time zone. And if you're on Twitch, you can, subscribe here, follow whatever, and get all that, and you get the updates as well online. And if you're watching my backups and my videos on YouTube, you know what to do there. Hit that subscribe, like, thumbs up, leave a comment, all that stuff. And yeah, what else? Oh, the link above my head, that goes to a site called declarative.tv, and there are lists of other streamers who are doing stuff in other declarative style programming languages, like Haskell, but also stuff like Erlang and whatever. So you can find a lot of people that way if you're interested in those kinds of languages and that kind of programming. And there's also a link to a Discord server there as well with a channel for this stream. So if you're watching on YouTube in a different time zone and you still want to chat and hang out, ask questions about things you've seen or whatever, you can ask those there. And just hang out with some of the more community-oriented channels as well. And all the code for tonight. I'm going to stash this here. I'm going to push it up, but the code for tonight lives on GitHub. Big long name. I'm going to push it up, and it lives on GitHub. I'm Agent Ultra there as well. And in most places around the internet, I would say. There's a wave function collapse. So if you want to check that out, follow along, whatever, you got it. Cool. All right, let's go find someone to raid, and then I'll see you next week. So may your types always check. Or may your monads always be free and your types always check. That's usually what I say there. That's the tagline. Okay. Hopefully we don't get anything weird. Retro FPS game dev. Sounds cool. Jitspo. Okay, Jitspo, we're gonna dive in, and everyone here, raid. Make sure to be friendly and give them a follow if that's the kind of thing you like to do. Let's go. Let's start. All right. Thanks again for tuning in and watching. It's been a blast. And here we go. Rating.